First is our irreversible process. So what is irreversible process? It's a process where you can't change its state one its final state is achieved. That means suppose you are holding a stone like this, but if you break it like this in many parts, so in this process if you join them, okay, you can join them perfectly. So what will happen? You will get something like this if you join them, but the round state of that stone will not be achieved again. So what this process will be called then? Because its final state can be reversed and go to the initial state, so it will be called our irreversible process. So that's what happening in heat also. Okay, they can once their final state is achieved, they can go to their initial state. So here one thing happens, that external pressure or P external will be constant. So throughout the process, okay. So here we have a formula for work done of irreversible process, that is minus P external into V2 minus V1. So what is V2, what is V1? Let us draw a graph, we'll understand from it. Okay, so here it is P external, which is constant, that is why it is straight line, but volume is changing here. So suppose this is V1 and the volume is changed, now it is V2. Okay, so here from B it is going to A. So what is this shaded area will be then? It will be our W irreversible. Okay, so that's how we achieve this part. It is minus P external into V2 minus V1 equal to W irreversible. Now you are gonna see what is the work done of reversible process. So you can just guess it from the name that what will be the reversible process and why it is called reversible, because the process which take place in infinite number of state such that the system and surrounding remains in equilibrium throughout the system. Okay, that's what the process are known as the reversible process. So its definition is not that important, so that's why I'm not writing it, but there is one factor, that is W reversible or work done of the reversible process is greater than work done of irreversible process. Okay, so that's how. Then so let's see the formula. W reversible with respect to our volume. Okay, what will be the formula? minus 2.303 nRT log V2 by V1. So I am writing here V2 by V1. So what is V2? V2 is the final volume V, and V1 is our initial volume. Okay, just remember that. And W reversible with respect to pressure, what will be it? It will be minus 2.303 nRT log P1 by P2. That is, previous one is V2 by V1. It is now P1 by P2. So you can just guess that this P1 is initial pressure and this P2 is final pressure. Okay, so it's also done. Now we are gonna see work done in various processes. So we have seen reversible and irreversible. Now we are gonna see what happens if this reversible thing happens in isothermal process, and irreversible thing also happens in isothermal process. Let us see that isothermal process. So what happens? This here isothermal process, it doesn't allow a change in the temperature. Okay, so if we write the equation what we achieved in mathematical expression of first law of thermodynamics, so del U will be 0 because there will be no change in temperature, so no change in the internal energy, so del U equal be 0. So 0 equal be Q plus W, or Q equal to minus W. So here work done in this isothermal process, okay, will be minus of the heat exchange. So what happens if we write it like this, minus Q, that is also valid. So the work done in irreversible isothermal process will be, the minus sign will be gone and it will be only P external into V2 minus V1, and also the same for W reversible, the minus from the front will be gone and it will be 2.303 log V2 by V1, or 2.303 nRT log P1 by P2. So work done in isothermal process is done. Now we're gonna see what happens in isobaric process. Okay, so let's see that isobaric process. So in isobaric process, what happens that here del P equal to 0. Okay, so if we just write the expression here, so you will see U2 minus 1, that means changing the internal energy, you write it like that, minus P external into V2 minus V1. So it will be like this, U2 minus U1 into QP, P minus PV2 minus plus PV1, right? So here, if we just let the QP remain here and just place it here, so it will be U2 minus PV2 minus U1 minus PV1 plus PV1. right? So what happens? We can write it like this: H2 minus H1, because you can see it here, that is also heat and it is also heat. Whatever happens, QP equal to del H. That means heat exchange will be the change in the work done, or work done will be the change in the heat. Or we can also write it like this: the heat exchange at constant pressure equal to the change in enthalpy of a reaction. Okay, so work done in isobaric process is also done. Now what comes is our isochoric process. So let's write it down. Isochoric process. So what does this isochoric process say? That is, we all know del V equal to 0, then W we all know that P del V. So that will be also 0. So del U equal to will be Q. Okay. Now here we will add a V here, because this V means heat exchange in constant volume. Okay. Now we are gonna see a relation between the del H and del U and del P. Now you are all thinking what this del U, del P, del V is coming, right? So let's see it. In cyclic process, what happens? The equation of first law of thermodynamics comes like this. Okay, because the final state and initial state is same, so there is no change in the internal energy. So that's why the del U equal to will be 0. So here a equation comes from this equation, that is del H equal to del U plus P del V. Now we can write this del U as it is, but this P del V can be written as like this: P2 V2 minus P1 V1. So you are just from this can conclude that this is the final pressure and final volume. This is the initial pressure and initial volume. So here we can convert it in another type of equation, that is del Ng RT. Now you are all thinking that what is this del Ng? So let us see a equation here. Okay, N2 plus 3H2 forms 2NH3. You all know. And this is a gas, this is a gas, and this is also a gas. So del Ng, that means change in the atoms of the gaseous product and gaseous reactant. So it is always will be Np minus Nr. That means product, sum of the atoms of the product plus sum of the atoms of the reactants. Never do it opposite, because the sign will change then. Okay, so it will change all the reaction and your answer, and your answer will come wrong. Okay, so here what will be our del Ng? It will be here 2 and here -1 for N2 and -3 for H2. So it will be -2. Okay. So now we are gonna see some relations according to this reaction. So first is our case 1. What will be that? That is, if this del Ng equal to 0, then del H equal to will be del U, right? You can see it from this reaction. Case 2, if del Ng greater than 0, then what happens? Del H becomes greater than del U. And in case of case 3, if del Ng is less than 0, that's what happened in what we have shown you in the nitrogen to plus hydrogen to ammonia formation. The del Ng came in minus. So then del H will be less than del U. So you can see that del H is here is synonymous with del Ng, because if del Ng greater than 0, del H greater than del U. Del Ng less than 0, del H less than del U. So here our cyclic process and all the things according to that is done. Now we'll come to heat capacity. Okay, heat capacity. Now, what is this heat capacity is called? So, to know the heat capacity, we have to know a certain thing, that is a relation that the increase in temperature is directly proportional to the heat supplied. Okay. Now, just write it in mathematical form. Del Q equal to directly proportional to del T. So Q will be here C del T. C is a constant here. To remove the proportional sign, we have to add a constant. So we added the constant here, C. So C is equal to Q by del T. And this C is our heat capacity here. So you all understood how this heat capacity came here, right? Now, regarding to this heat capacity, there are certain relations. So we are going to see that. So what will be it? First relation, here is our del H equal to NCP del T. Now we are all thinking that what is this CP? This CP is our heat capacity at constant pressure. Okay. And next is our del U. So it will be NCV dt. So you can also guess from the previous that it is heat capacity at constant volume. So relation between Cp and Cv, that will be Cp minus Cv. What will be it? Will did I conclude it from here? So you all know del U equal to Q plus W. So what happens when this Q comes to this side? You can also write it like this. So it will be like this, NCP dt minus NCB dt equal to our NR dt, right? So here dt is cut, n is cut. So what remains? Cp minus Cv equal to R. That is the relation. Okay. Now we are also gonna see another relation here. That is Cp by Cv equal to gamma. Okay. So there are some things that you guys have to know, because it directly asks in the neat questions that for your monoatomic gas, this Cp will be 5 by 2R, it will be 3 by 2R, and this will be our 1.66 gamma Cp by Cv. And for diatomic gas, it will be 7 by 2R, it will be 5 by 2R, and it will be 1.4 for diatomic gas. And next is our for triatomic or polyatomic gas, that is 4R, 3R, 1.33 polyatomic or triatomic gas. Okay, work done. So let's write it. Irreversible adiabatic process, work done. Okay, so what will be its value? It will be nr gamma minus 1 T2 minus T1. That T2 is our final temperature, T1 is our initial temperature. So if I have written this at first, you won't understand. So I have shown you what will be the gamma and their values. So here is a thing that if this T2 is greater than T1, okay, so there will be no change of signs. The W irreversible will be positive. Okay, so that happens in our compression. Okay, because in compression the work done is positive, hence the final temperature will be greater than the initial temperature. Because we have told it. Now because of this, what happens, that heating of the gas occurs, because final temperature is being more than the initial temperature, so heating of gas occurs. These questions asked directly in the NEET. But if T1 greater than T2, then W reversible will be here minus V. So what is happening here? Expansion of gas. So cooling of gas occurs here. Okay. So it is for irreversible adiabatic process. Now we are gonna see for reversible adiabatic process. Reversible adiabatic process. Now for reversible adiabatic process, there are three formulas you have to remember, and that will be sufficient for this topic. That is, first one is PV gamma equal to constant to the power gamma. Okay, PV to the power gamma, PV to the power gamma. This to the power is upon V. Okay, also here is also to the power is upon V will be constant, and here P to the power 1 minus gamma T to the power gamma equal be constant. Now here, from here we can also deduct the equation that P to the power 1 minus gamma will be 1 by T to the power gamma, or we can write it like this: P equal to 1 by T to the power gamma by 1 minus gamma. So to write it like that, we will just have to change the equation, and you can just go for any sum from this. Okay, so here our reversible adiabatic process is also done. So now what comes, that is our enthalpy. Okay, so what is enthalpy? Let us discuss that first. That is enthalpy. Now enthalpy means that if the heat exchange or heat uh, change in a reaction. So this enthalpy are of different types. Okay, so first is the enthalpy of reaction. Okay, enthalpy of reaction. So here enthalpy of reaction, what is, does it mean that enthalpy of reaction, since every reaction takes place at constant atmospheric pressure, there we can are only concerned about the enthalpy change only, right? So let's suppose that a reaction is forming here. Again, we are writing the reaction for ammonia formation. We can also write it like this, right? Right or wrong? Right, right. So enthalpy of reactions formula will be del H of R, that is summation of all the bond energies of the reactants. Okay, bond energy of reactants minus summation of bond energy of products. So here our enthalpy of reaction, we can just guess it that if some value is given here for n bond in NH for H and this NH, so we can just place the values, and from this formula enthalpy of reaction will come out, right? Now comes our enthalpy of formation. Okay, so what is enthalpy of formation? Enthalpy of formation. Now this enthalpy of formation is very important. Okay, that is the change in the enthalpy formed when their constituent element in their most stable state. Okay, constituent elements are in the most stable state. So here it will be del HF, but what we are seeing it here, it will be del H of products minus del H of reactants. In previous enthalpy of reaction, we have seen that bond energy summation of reactants minus bond energy summation of products, but here happens the opposite thing, that is del H P of products minus del H of reactants. Okay, so in this enthalpy there comes a law that is called our Hess's law. So to learn about the Hess's law, let's draw a diagram. Okay, so what we are seeing, that this A is converted into B and the heat exchange here is H1, or enthalpy exchange is here H1, and from B to C it is H2, and from C to D the enthalpy change is H3. But what happens if we just directly change A to D, then let us suppose this reaction or del HF or enthalpy of formation is del HF. So what will be the del HF? So we can write the del HF like this. So what does it mean? That means if a process is achieved by multiple steps, so the enthalpy change in that steps, okay, the sum of their enthalpy changes can be directly equal to the del H formation of that reaction. Okay, so now we have to know some properties here. What are those properties? Let's see. See, let's write properties. Now for properties, what we are gonna see here, that let a reaction is like this, A to B forming C, the del H is let plus N. Okay, but what happens when the reaction is getting reversed? Okay, then del H dash will be our minus N. Got that? If the reaction is reversed, then the sign is also reversed. Okay, now if we just multiply this reaction here, what will be it here? It is also get multiplied. Okay, so the new del H enthalpy will be twice of the previous enthalpy. So these are the things we have to remember when solving any equation that is given to you in the NEET question. Okay, so next comes our heat of combustion. So let's first delete it. Let write heat of combustion. So what does this heat of combustion do? That the amount of heat released when 1 mole of compound is big completely excess of O2. That means completely used by O2. Okay. So the calorific value has a formula according to this heat of combustion, that is del H of combustion or enthalpy change of the combustion, that will by molecular weight of that fuel that is causing the combustion. That will be the calorific value for this reaction. Now there is one thing that will be called enthalpy of neutralization. Now what is this thing? That is, if a strong acid and strong base, or a strong acid, weak base, weak acid, weak base, if acid or base is taking part in a reaction, some heat gets evolved. Okay, so this heat which is evolved, that is causing change in the enthalpy, that change in the enthalpy is called our enthalpy of neutralization. So for strong acid, it will be our minus 57.1 kilojoule per mole. Strong base also gives the same value here, but this value can be written as with respect to kilocalorie also. That is minus 13.7 kilocalorie per mole. Okay. So what happens when this strong acid or strong base is not taken? That means if any weak acid or weak base is taken, so then the value comes, let's write it, del H newt minus less than minus 57.1 kilojoule per mole. Okay, so here enthalpy of neutralization is done. Next comes our enthalpy of atomization. So let's write it down. Enthalpy of atomization. So what is enthalpy of atomization? The amount of energy released when 1 mole of compound is dissociated into a constituent gaseous atom. Okay. So let's write it. Amount of heat released when 1 mole of compound is dissociated in its constituent gaseous atom. Okay. So questions from this atomization doesn't come. So don't have to remember anything. I'm just telling you because these are all included. So next is our enthalpy of solution or heat of the solution. Let's write it down. Enthalpy of solution, that is, if a solvent and solvent plus solute, we know forms what? Solution. But forming this solution, there is the change of some thermal energy, or there is some heat evolved or heat is absorbed. So that change in the enthalpy is called enthalpy of solution or heat of the solution. Okay. So from this enthalpy of solution, we can also derive that if a solute is soluble in a solvent or not. So let's write the formula first. That is del H solution equal to del H lattice plus del H hydration. Okay, this is the standard formula. Now what happens that if this del H lattice is greater than this del H hydration, so the solute becomes insoluble. That means it doesn't gets dissolved in the solution. But if this del H lattice is less than del H hydration, that's when it becomes soluble. Okay. So here is our regarding everything. First law of thermodynamics is done. Now comes our second law of thermodynamics. But to learn the second law of thermodynamics, we have to know a particular thing that is called our entropy. So let's write it down. Entropy. So what is entropy? That is the degree of randomness present in a system is known as entropy. That is the degree of randomness present in a system is known as entropy. Now this entropy is shown by S, but we can't conclude the entropy, but we can conclude the change in the entropy. So change in the entropy will be that is del S, so it will be change in entropy. Now we are gonna see that this change in the entropy, it can be happening for universe. So what is del S universe? There is some system in this universe. So the change in the entropy of that system will be del S system, and change in the entropy other than the system will be change in the entropy of the surroundings. That will be our del S surroundings. So del S universe is del S system plus del S surround. So what does the second law of thermodynamics say? It says that in any process, del S universe will be greater than 0. That means the entropy of the universe is always increasing. Okay, it can neither be decreasing, it is always increasing. Now to discuss this del S here, we have to know that what is this del S. So that is our Q by T. Now we are going to say what is Q. We have already know this Q is del H, so it will be del H by T. Okay, so it will be our formula for entropy. Now there is something called spontaneous work and non-spontaneous. So let's see it. Spontaneous work. So what is spontaneous work? This kind of works happens without starting it, or what can I say, that require, it doesn't require any driving force. Okay, it just happens naturally. But so it happens naturally. So all naturally occurring processes are spontaneous. So what is non-spontaneous work? So for non-spontaneous work, you need a driving force. That means it doesn't wanna happen, but you have to force it for happening. Okay. So now for this spontaneous and non-spontaneous work, there is a thing we call that is del S. Del S for spontaneous work will be always greater than 0, but del S for non-spontaneous work will be less than 0. Now here comes a reaction that is our called Gibbs-Helmholtz reaction or equation. What does this equation say? This says that del G of system is equal to del H of system minus T del S of system. So for spontaneous work, this del G is always will be less than 0. So what we are seeing it here, it's for spontaneous work, del G will be less than 0, del S will be greater than 0. Okay, always. Now, what happens in the equilibrium process, in equilibrium condition, this del G becomes 0. So here H equal be T del S. So that's how we derive the formula of our entropy. In the previous case, we have shown it. That is del S equal to del H by del T. But from here, we can also deduct a formula then. That is del G is less than 0. So del H minus T del S, that will also be less than 0. Right? So these are separate. What happens? That del H is less than T del S, or we can write it like this, that T is greater than del H by del S. Now this is a very important formula for neet because they will give you a enthalpy change and entropy change. Okay, value, numerical value. Then they will ask you, tell us that this on which temperature this process will be spontaneous. So you can just derive it from this formula. Okay, that whatever the temperature will be given in the answer, that will be greater than the temperature derived here. Then the process will be our spontaneous. Right. So there are some certain things we have to also see from it, that in equilibrium we have seen that this del G is 0, but this del G has another form of reaction, that is del G equal to del G naught plus 2.303 RT log Q. Now in equilibrium this will be 0, so the reaction comes like this, del G naught equal to minus 2.303 RT log Q or K. Okay, so this is also a very important reaction. Now there are some certain cases. Okay, so for the case 1 where del H is greater than 0, del S is also greater than 0, then T del S is greater than will be del H according to the reaction. We're writing it again here, del G equal to del H minus T del S. Okay, so from this we can conclude that in high temperature this will be spontaneous reaction. In case 2, where del H is less than 0, del S is also less than 0, then T del S will be less than H. So here at low temperature, it will be spontaneous, right? So these are the cases. Okay. So here is our thermodynamics is done.